Я думаю, что мы начнем. So, can I ask you a few words about you? Because our tradition, but could you introduce himself?
Okay. Yeah, so I am Pierre Dehornoy. I am a French mathematician, usually in Grenoble, in the south, in the Alps. But now I am for 6 months at the independent university.
Please.
Thank you. So my talk will be about three-dimensional topology and dynamical problem. So here is the main topic. So it will be about three-dimensional flows. And in particular, three-dimensional Anosov flows. I will recall what it is. So what I would like to state is to state some conjectures and some partial results toward this conjecture, and if I could interest you to that conjecture, I would be interested. So the main problem is, so we have a three-dimensional vector field, so X, so on a manifold M. So in general, here we will assume that X is non-singular, and that M is a compact oriental. So, in general, yes, but let's say it can have boundary, and the vector field has to be tangent to the boundary in that case.
Not singular, you mean no zero?
Yes, so I mean for all X, the vector field is non-zero. Yes. So this is the general framework. And so when you have a vector field, in general, you consider phi t the flow generated by the vector field. So you have
So you fixed the compact.
Well,
or no?
Well, no. In general, well, it will change. There will be several compact.
Because if M has a boundary, you must consider the special condition of vector fields.
Tangent.
Tangent.
Yes. If the boundary of M is non-empty, then X is a tangent. Tangent
to boundary. Yes.
To the boundary.
Yes. It's important. Okay.
Yes. We cannot escape.
Oh yes.
Do you work with continuous vector fields?
Yes, continuous.
Yeah, of course.
There was condition. Okay. Yes. So in general, you have the flow. So what is the flow? It's just if you have the vector field at some point. Here, this is the vector field. Phi t describes the orbits. So here you have phi t of x, which is just where you are after time t. So probably it means that if you look at the derivative here, it's exactly the vector field at that point. So the derivative of phi t is exactly the vector field. Okay, so in general we have that, and we want to study these objects up to diffeomorphism. So this means that well, we will introduce a special. Here we are interested in topological properties, and in particular we are not really interested in the parametrization of the flow. So we will say that x and y are flow equivalent if there exists a diffeomorphism that transports orbit of x onto orbits of y. And when I say transport, it means that the time can change. So in other words, what we say is that the vector field transported by f is proportional by some function here to the vector field Yes. So what we want is to consider these things up to time reparametrization. And we ask the question, well, the general question is where are two such flows equivalent or not? So this is a very general question, and we will restrict our attention to a special class, which is Anosov flows. So we recall what Anosov flows are.
So there is nothing which is specially three-dimensional.
No. Here this is general and well.
Yes.
The problem will be three-dimensional because in higher dimension it is in a sense solved. So this is a specific dimension 3 because of that. Well, I mean, it depends on what you ask. Of course, in general, the problem of equivalence is complicated, but here.
Lambda is positive, yes?
Yes, lambda is positive. Yes. So, what is an Anosov flow? An Anosov flow is a particular flow. So I will give the definition in dimension 3, although it can hold in every dimension. It's a flow such that the tangent space to the manifold splits into the sum of three bundles. So at every point x, you have the direction of the flow of the vector field, and you have two transverse directions, which are called the strong stable and strong unstable direction. Here, since dimension is 3, these two have to be one-dimensional. And what does that mean? Well, what it means is that here, if you take a point in that direction, so what we have is that the flow contracts that direction, the stable direction. So what it means is that if you look at the space derivative of phi t, okay, and you restrict it to this direction Es, then this is constructed. So in positive time, the flow contracts this direction. Well, I should put the norm of. No, that's okay. So this direction is contracting in positive time. If you integrate that, that means that if you start from a point here, you look at the orbit here, this orbit, all these orbits accumulate in positive time.
What about alpha?
Alpha is a positive constant. Yes.
It is Majoran for.
Oh no, yes, sorry. If I say that, I should put yes. Yes. And the same holds in the unstable direction, but with negative times. So what we have is the same thing. So this time, in negative time, we have the same thing in the opposite side. And so this means that if you look...
The same, minus beta.
No, because now t is negative.
Okay. Okay.
So here we have this point, we have the flow direction here, and we have another direction, the unstable direction. And now if we go backwards, this thing converges in the past. So we have two directions, say here vertical and horizontal. In the positive we converge, in negative we converge in the other direction. Okay. So this is the general class of Anosov flows, and these flows are, well, very interesting and important. Interesting because there are many of them, and also because they were the first, well, I don't know whether they were the first, but they were an historical example of chaotic systems. So here, of course, if you take two points which are close, except if they lie in the same, on the same vertical line, the orbit will diverge. So they present a chaotic property. But on the other hand, it was shown by Anosov that Anosov flows are structurally stable. So it's a remark that is important for them. Anosov flows are structurally stable. This means that if you perturb a bit the vector field, it will stay Anosov first. If you perturb in the C1 topology, it will stay Anosov first, and more importantly, what you obtain will be conjugated to the initial flow. So if you perturb a bit the flow, you don't really change the dynamics. You change the dynamics at that point, but then if you switch a bit, you can observe the same dynamics. So these objects are, well, they present a chaotic behavior, but they are structurally stable, so it's a nice object. And yeah. Well, and they are also important in topology because they help in the problem of classification of manifolds and things like that. I will not come to that, but we have that in mind. Yes?
You perturb C0 or C1?
C1.
C1. As the field is C1?
Hmm?
The field is...
yes,
C1?
Okay, I will try to not to say... Yeah, I think you consider C1 vector field and you perturb in the C1 topology. Yeah, let's... Okay, I'm not 100% sure of that. I am sure you perturb in the C1 topology. I don't know what is the regularity of the vector field. Which regularity you require. Yeah. Okay. Okay. Let me present, so now the first important example of Anosov flow, which is given by suspension of automorphism of the torus. So, what you do is you consider a 2x2 matrix whose trace is larger than 3. So, when you consider such a matrix, it acts, of course, on the plane, it acts on the integer point, so it acts on the torus. So what you can do is you consider the torus R2 like that 2, and A that acts like that. And so what you consider is the suspension. So just this torus times the interval. But instead of gluing, so you glue a point here on the top, instead of gluing by the identity, you glue using your matrix. So here you glue these two faces using the matrix A. Okay. So in this way you obtain a 3 manifold, and it supports a canonical flow, which is the vertical flow, which I will denote just by T over Z. So here I have a 3 manifold with a certain flow, and what I claim is that this flow is of Anosov type. And how can we see that? Well, we have to use this hypothesis because in this case, what do we have? We have two eigenvalues. We have eigenvalue lambda larger than 1 and 1 over lambda. And we have some eigendirections here and there. Yes, so we have one direction that is contracted, one that is expanded. And now if we look at a point here, if we look at its orbit, it will converge here to 0. Which means that here, if you consider the lift here of this direction, and you consider a point here, well, you consider, here I consider the point 0, 0, so this orbit here is periodic. And here, this orbit, well, it goes here, but after it comes back here closer, and closer, and closer, and closer, and you see that this orbit in positive time converges to that one. And actually converges asymptotically, because here points converge to 0 asymptotically. Then if you translate that, if you take any 2 points here, which are related by this direction, well, this point will have a certain trajectory, and the trajectory on that point will converge to the trajectory of the initial one. Okay, so the orbits here, if you take 2 points which are on the same plane here, their orbits will converge in positive time. And now if you do the same but in this direction and you look in negative time, you will obtain the same picture. So these two stable and unstable directions by the eigenvectors associated to the two eigenvalues of your matrix. So this is the main example of Anosov flow. Okay. And yeah. Okay. So this is the main example I am interested in. So what I said is that in general we want to solve the problem of classification. So here we can first ask what is the classification of this flow up to conjugacy, up to flow equivalence, and this classification is very simple. So here we have a, it's not very bad. the classification is the following. So here I will call this manifold MA with the suspension flow. So this is called the manifold MA. And so we will have that, well, here MA with this vector field, with this vector field is flow equivalent to MB with the vertical vector field. If and only if what? Well, if and only if the matrix A and B are actually conjugated inside integer matrix. So not exactly. If there exists a matrix P with determinant plus or minus 1, such that A equals P inverse BP, or well, actually it's conjugated to the inverse one. So, well, here, actually, this problem, it's not really a problem about vector fields, because actually it's already a problem about these three manifolds. We can wonder when are these two manifolds the same, and the answer is exactly this one. So there is an easy and a difficult one. There is an easy and a less easy direction, but not difficult. The easy one is if two matrices are conjugated like that, then the flow are equivalent. Because actually the action of A and B on the torus is the same, except in different bases. And then you transport that and you obtain the same suspension. So the proof of, well, that direction is easy. And for that direction, well, then you can wonder. And for that direction, if the flow if there is a flow equivalence, then the manifolds are diffeomorphic. So in particular, you have that MA is diffeomorphic to MB. And actually, this problem can be solved at the level of pi 1. Because if you look at the pi 1 of MA, this is actually an HNN extension of Z2. So you have the Z2 factor, the horizontal one, and then you have to glue the top and the bottom side together. And this is an HNN extension by the matrix A. And actually you can prove, well, I will not do it, but you can prove that actually these things are, so you can prove that then pi 1 of M is isomorphic to pi 1 of AB. Here, if and only if you have that. So I will not do that, but this is just at the level of pi 1 that we calculate. Okay, so here the problem of flow equivalence of these examples here of another flow is solved. But then you can ask the question, are these flows really different? I mean, can we relate them in a weaker sense? And this is what this talk is about. So there are two natural ways of relaxing our notion of equivalence. The first relaxation is what is called commensurability. Commensurability is what involves finite coverings. So you will say that here two flows, you will say that a manifold with a certain flow is commensurable to another manifold if there exists a third manifold that covers both. So we write it like that. And here what does that mean covers? It means that here you have a finite covering. So K21, K521. You have a finite covering, and what you do is that this covering sends this vector field to a multiple of this vector field. Again, this is in the sense of flow, so you can reparameterize, but that's all you can do. So you sense orbit of that one and orbit of that one. So this is the first natural relaxation things, and then you can wonder what are the equivalent. So this is an equivalence relation because these coverings are finite, and then you can wonder what are the equivalent classes here. And I will introduce the second natural one, and then I will state the questions. The second one is almost equivalence. And what is almost equivalence? Well, equivalence is you send orbits of one flow into orbits of the second flow. Almost equivalence is the same up to something, up to removing some finite number of periodic orbits. So almost equivalence here, it will be, there exists gamma 1, gamma n periodic orbits of the first vector field. There exists, well, psi 1, psi n periodic orbits of the second vector field, such that what remains on when you remove this vector field, these periodic orbits is almost equivalent. So is equivalent. So this one M1 and this is M2 minus. Okay. So here in this notion of equivalence, you have some for example in our example we know that here the orbit of the point 0, 0 is a periodic orbit, so you can remove this periodic orbit. Then you obtain a flow on a non-compact manifold, but actually you can blow up this orbit rather than removing it, and then you obtain a flow with a nice boundary. And in this case, you can ask the question of almost equivalence. Okay.
The question.
Yes.
Number of orbits must coincide.
Yes, because then the number you will obtain two manifolds with boundaries, so at least the number of boundary components should be the same. So this is why here this is n and n. So I will now I state a very optimistic conjecture. Well, it's still a conjecture. I don't know whether it's true or false, but I think it's optimistic. I have very little hope it is true, but I think it's a nice conjecture that all transitive Anosov flows are almost equivalent. Okay, so here I've presented Anosov flows. Transitive just means that there is a dense orbit. So it is, for example, the case of these torus suspensions. You have dense points when you iterate the automorphism of the torus. So these flows are transitive Anosov flows. There are many others. We'll see a second class later. And this very optimistic conjecture says that if you take any two Anosov flow, you can remove finitely many periodic orbits on both sides and obtain the same flow, the same manifold. I don't really believe in this conjecture, but I don't have any counterexample yet. So, okay. So this is the main conjecture I have in mind, and I would like to disprove it. Okay. But now, what you can do, we will come to that in a moment. Well, at the level of commensurability, there are many classes. Yes, if you can ask the same conjecture with commensurability, and then the answer is no. And we will see that in a minute. But then what you can do is to combine these two notions to obtain even a weaker notion. So the weaker notion is almost commensurability, which means you have two flows, and you can do these two operations, which mean you can remove some finite number of periodic orbits, then take some covering, then maybe remove still some finite number of periodic orbits, and obtain the same flow and the same manifold. So the third notion is the notion of almost commensurability, where what you can do is combine commensurability and almost equivalence. So this is a weaker notion, of course, than commensurability and almost equivalence. And you can use them, which means you can start from one, remove finite number of periodic orbits, take a covering, remove, take a covering, and so on. So this is also an equivalence relation. And so you can ask what is the set of classes of Anosov, at the level of Anosov flows, what do you obtain? So I can state a conjecture in which I strongly believe, which is that all transitive Anosov flows are almost commensurable. So this conjecture is also still open, but this one I strongly believe in. And what I would like to do is to prove a particular case of this conjecture that I will now just state, is that this conjecture is true for suspensions of automorphism of the torus. So all suspensions of automorphisms of T2 are almost commensurable.
Do conjectures consider all the flows on the same manifold?
No, because when you remove some periodic orbit, you change the manifold. And actually, we will encounter some examples. Well, here you can see that the manifolds will not be the same. As I said, two suspensions of torus automorphisms are on the same manifold if and only if the matrices are conjugated. And there are many conjugacy classes of matrices, so not all matrices yield the same manifold. But if you take coverings and you remove some orbits, you completely destroy the topology, I mean some of the topology, and then, well, we don't have a counterexample at this level. So, yes. So this is okay. So this is the two conjectures I have in mind, and this is just a particular case of that one. But I think that the road to this conjecture introduces some nice ideas for these general fields. So what I would like to do is to explain that.
But we additionally require that the flow is transitive here. Yes?
Well, here these flows are transitive, and here, yes, here I add the hypothesis I consider transitive Anosov flows.
And if you take an automorphism, it does not, or it is always give, it always gives you a transitive.
Yes. True. Automorphism of the torus with trace larger than 2. Hyperbolic automorphism of the torus are transitive.
If you just rotate it by 90 degrees.
Yes, but this one does not have trace larger than 2.
Ah, trace larger than 2. Okay, trace.
Another very simple question about this periodic orbit. Then, if you're on the same manifold, you claim that all Anosov flows on the same manifold, they have the same amount of periodic orbit.
No, I don't claim that. First of all, transitive Anosov flow have infinitely many periodic orbits.
Yeah.
So, second, I don't claim that on the same manifold the flows are the same. I say that on the same manifold, maybe you have to remove some finite number of periodic orbits to obtain the same flow on the same manifold. Well, actually, I could say that in my introduction of Anosov flows, that it is a theorem of Thurston, I guess, that every hyperbolic manifold admits finitely many Anosov flows. But this number could be 0, it could be 10, or it could be 1, but it's not always 1 or 0. So a certain manifold can admit different Anosov flows. Yes, okay. So, yes. Yes. Okay, so first I would like to stay with, I would like to explain you the commensurability class of automorphism of the torus. Because, well, this will be important. So, as I said, equivalence class corresponds to conjugacy classes. So maybe you wonder what are conjugacy classes of hyperbolic matrices. For example, if you look in trace 3, there is only one conjugacy class, which is this one. Every matrix with trace 3 is conjugated to this matrix among integer matrices. Okay, but for example, if you go to trace 5, there are two conjugacy classes. I mean, you actually have to write that one, so it's conjugated to the previous one. But if you look in trace 5, no, trace 6, there are two conjugacy classes which can be represented by this matrix and this matrix. And you can try to prove that these matrices are not conjugated, but they have the same trace. So, and the situation is that in every trace you have finitely many conjugacy class, but this number is not 1. Okay? Because you cannot. Okay, so this was the first remark. Okay. We know that here all the matrix conjugated to that one is the same torus automorphism. Now there is one remark that if you have two matrices such that who have a power which are the same, or say conjugated, yes, where P has determinant 1, if you add that, then the suspensions are commensurable. So here I take the suspension and the vertical flow. So the suspensions are commensurable. Why so? Well, I have to find a common covering to these two things, and this covering is given exactly here. You take the suspension. So here what you do is that you take I copies of the torus on this side. So I copies of the torus, and you group them by AI. Yes? So here I equal 3. And you know that this thing is just, well, by our theorem, you know that this is the same thing as taking J copy and gluing here by Bj. Okay, so here what you just take the suspension of AI and Bj, and you know that these are the same. And now this one is a 3-to-1 in this case cover, or just the suspension of A. Yes. Because here you can project each block here on that one, and since you glue by AI, here you glue by A. Yes, and on the second, on the other side, you glue by B. So here, if two matrices have a power in common, then these things are not necessarily equivalent, but they are commensurable. Yes. So you can ask the question, where do two matrices have the same power? For example, do these two have a power in common? And the answer is no, actually this does not really help. For example, this one squared gives you that one. So these two things are commensurable, but these two are not. Okay, so we need something more. And there is a second remark that will allow us to connect these two matrices here. How do you connect them? Well, actually you can look. A way to do that is to know that these matrices are conjugated, but not with integer coefficients, with rational coefficients. In other words, if trace of A equals trace of B, there exists P with integer coefficients, but not determinant 1, such that PA equals BP. In this case, for example, you can check. Yes, you can check that you have that 5, 2 to 1 times, where is the 2? Times the diagonal matrix 1, 2 is equal to the diagonal matrix 1, 2 times this one. And it is true that when you have the same trace, you can always find these things. So this is the matrix P. And now what do you look? You look at the lattice P times Z squared. So this is a sublattice of Z2. And now what you know is that if you look at an element of this lattice, and you act by B on this element, so you have an element in the lattice, which is of the form Px, and you act by B, then by hypothesis, this is also P times A of X, so this lattice is invariant by the action of B. Yes? So here, if you take these things, you have your lattice Z squared, and you have the sublattice generated by this matrix. Just take every second row. And in general, this sublattice is not invariant by an integer matrix, but here by this assumption, it is invariant by B. So now you have two things. You have two quotients. You have the quotients R2 over Z2 as before, and you have the quotient R2 over PZ2. And both these quotients are both invariant by B. Yes. And now you look how you act in the canonical basis here on that lattice. Well, you act by B. But now in the canonical basis of this lattice, which is this basis, the basis given by the two columns of this matrix, if you look at this action is actually given by the matrix A. Because if you will, this is exactly this equation here. Which means that actually here, since this lattice, this one here, this one has fundamental domain like that, this lattice is another 2 cover of that one. Actually the torus associated, this torus is another 2 cover of that one. So you have a 2 cover here, and on these 2 cover, B acts here by A and here by B. So this gives you commensurability. Here you have a 2-to-1 commensurability between the suspension of A and the suspension of B. And this is always the case. So this means that actually if trace of A and trace of B are equal, then the suspensions are commensurable. And now we can state the theorem. the theorem is that the proposition is that the suspensions are commensurable if and only if, well, the log of the larger here, well, the log of the largest eigenvalues live in Q. Okay, so what does that mean? You see that when the trace is the same, oh yes, when the trace is the same, of course the larger eigenvalue is the same, so this ratio is just 1. And now if you glue that with the fact that AA equals BJ also gives you a commensurability, the fact that AA equals BJ can be read exactly like that. Yes. So this remark here tells you that actually for commensurability just the trace is enough. And the previous remark, this remark here, tells you that it is not the trace that is enough, but the commensurable, the log of the largest eigenvalue is enough. Okay, but still, so here we have a complete description of the commensurability classes, but there are infinitely many. For example, you will never be able to relate the trace 3 matrix with the trace 4 matrix. Okay? And one way to see that is, for example, to use entropy. Because, well, this log of the largest eigenvalue is actually the entropy, and with commensurability, entropy can just be multiplied, but it will not be, you cannot exit the rationality class. Okay. So, yes. Now I want to go to almost equivalence and to start playing with different traces. And what will be the main tool for that? It will be what is called a Birhoff section. So we'll introduce Birhoff sections now. And to introduce Birhoff section, I will introduce a new class of Anosov flows, which are geodesic flows. So I don't know if you all know what the geodesic flow is. I will explain that. So first, what is the geodesic flow on H2? So you have a certain surface. Here it will be H2 to begin with. And you look at the unit tangent bundle. So the space of length 1 tangent bundle. So here in the case of H2, this is just a torus. At every point you have a circle of tangent bundles. And now you have a well-defined flow on this unit tangent bundle, which is when you consider a point in this tangent bundle, it corresponds to a tangent vector here. And this tangent vector, well, you can always, through this tangent vector, there is a unique geodesic that goes here. So every tangent vector can be written in the form a certain point that is on the geodesic and the derivative of that geodesic. And now the geodesic flow is just defined as taking the tangent vector to that geodesic at time t. So here you have a tangent vectors, yes, and at time t, if you follow the geodesic flow, you are at another point of the geodesic with the tangent vector to the same geodesics. So this is how you define the geodesic flow on, well, you have to remember what is the direction, so it is on the unit tangent bundle. Now, so this is on H2, but what you remark is that now if you have an isometry that acts on this picture, this isometry will, these things will commute with this isometry. So what you can do is you can mod out here by any Fuchsian groups. So a Fuchsian group is a group of isometries of here, and so this will send geodesics and geodesics, unit tangent vectors to unit tangent vectors. So you can mod out by any Fuchsian group. And this gives you, so for every Fuchsian groups, you have a unit tangent bundle, and you have a geodesic flow on this unit tangent bundle. And what I claim is that, so you have infinitely many Fuchsian groups, so you have infinitely many manifolds and flows here. And what I claim is that these flows are also of Anosov type. And this can be seen visually as follows. If you look in H2, and you take a tangent vector, so it points to so it's on a certain geodesic. Well, what you can do is to look at the horocycle that is centered at the positive extremity of the geodesics here, and going through this tangent vector. And now if you look at all, So it is orthogonal to your tangent vector. And if you look at all these tangent vectors here, also orthogonal to the same autocycle, you follow the positive geodesics, then you know that you converge to the same point here, and you converge exponentially fast. Well, then two geodesics will converge exponentially fast. So this gives you the stable direction of this flow. These things are positively contracted. And for the unstable direction, you have to look in the past. So you can do the opposite. You can look at the negative extremity of the geodesics and look at those vectors that come from this extremity here. So here you have these two row cycles, and now you look at the vectors which are normal to these row cycles, and then give you the stable and unstable direction in the unit tangent bundle. Okay. So this gives you another example of Anosov. Okay. First remark is that here you can have some flexibility in gamma. You can perturb an hyperbolic metric and stay with another hyperbolic metric. So you can wonder how does the flow changes under such a perturbation. So say if you have a certain metric on the genus 2 surface, a certain hyperbolic metric, and another one. Yes, you can wonder how do these two geodesic flows speak to each other if you change the metric. And this is a remark by Birhoff that actually the geodesic flows are the same. They are the same up to reparametrization, which is exactly our notion of flow equivalence. So the remark of Birhoff that if the two, so if the two quotients are isomorphic, then the geodesic flows are flow equivalent. And the proof is rather simple. The idea is just that, well, as I said, Anosov flows are structurally stable. So if you perturb a bit the flow, you are still flow equivalent to your initial flow. So now, if you perturb a bit the metric, this will just perturb a bit the flow. So if you perturb a negatively curved metric, you have another negatively curved metric, and you will have another geodesic flow. But by structural stability of Anosov flows, you will still have a flow equivalent. So when you perturb a metric, you are still flow equivalent. And now what you have is that if you take any two metric on here an hyperbolic surface, they are connected by a segment of negatively curved surface. So you have the metric G1, you have the metric G2, and if you look just at the segment that connect them, so TG1 plus 1 minus TG2, this is a family of metrics. All these metrics are negatively curved. So here you have a path of negatively curved metrics. And by structural stability, along this path, all flows are flow equivalent. So for any two metrics, for any two negatively curved metrics, the flows are flow equivalent. So there are infinite. So there is just one flow for each type of the orbifold of the quotient. But now there are infinitely many types of quotients. For example, there are infinitely many surfaces. So this gives you infinitely many flows. But here what we can notice is that at the level of commensurability, this is not very rich, because at the level of commensurability, if you take any two orbifold, any two Fluxian groups, they admit a common covering. So at the level of commensurability, there is only one commensurability class of geodesic flows. Yes, so there are many flow equivalent classes, but only one commensurability class. Now what I would like to deal with is the notion of almost equivalence. Okay, and the main construction is a construction by Birhoff, so I will explain it on an example. Here is Birhoff's construction. So what Birhoff did is to start with a genus G surface, but let's make the picture with genus 2. And he constructed a certain surface in the unit tangent bundle to this surface. How is this surface constructed? Well, what Birhoff did is to start with a certain collection of closed geodesics. So here 6 in that case. So Birhoff considered a collection of six geodesics. He could have considered another one, but what is important with this collection? So it's a collection of closed geodesics that divide the surface into disks. So, well, into hexagons actually. So maybe I can make the picture. So this is your genus 2 surface. Okay. And the collection of geodesics look like that. Here you have to trust me. Okay. What is important is that this collection decomposes your surface into 4 hexagons. One here. Okay. One that contains the vertex of our decomposition, and 2 here. This one and this one. So 4 hexagons. So this is a certain collection of geodesics. I will denote it by gamma. And now what Birhoff does is to consider a certain surface that I will denote by S gamma, which is the set of those tangent vectors such that, well, the point here is on the geodesics, and V, the tangent vector, points in the black face, in the black part. What does that mean? You take these points here and you point those tangent vectors that point in the black part. And at every point of this collection, you take these things. So this gives you, I claim that this is a surface. Why is it a surface? Because if you look above here, a certain point, in the fiber of that point, so you have this picture, in the fiber of that point, this geodesics lifts in the unit tangent bundle to 2 orbits, which corresponds to following this geodesic from left to right and from right to left. And what I do is to consider exactly the set of tangent vectors that points in half of the directions. So this corresponds to taking in the fiber exactly half the vectors which are between that point and that point. And then there are other vectors that we do not consider. So here this corresponds to vector pointing here behind the blackboard. And then there is the rest of the fibers that point in front of the blackboard that we do not consider. So here, this Birhoff surface is exactly this ribbon here in the fiber. So above every segment here, what we have is a rectangle. A rectangle that occupies exactly half of the fibers, because there is the other half here that we do not consider. And then, well, I say we consider that. Maybe we can look at what happens at double points, and I can reassure you what happens at double points is okay. Well, basically, the picture is that one. So here you have another geodesic that comes somewhere. This is the fiber of the double point. And what you have is you have this ribbon here that comes from those vectors here. Okay. So this other geodesic is oriented like that. And here, in this other part, this goes on. But here you look at, since here the black faces are always opposed at the vertex, here you consider vector pointing in the opposite direction. So here you have this ribbon, and here you have the ribbon, but it does not go on. It takes exactly the opposite part of the fibers. So you have one ribbon on the right, one ribbon on the left, and now you have 2 ribbons corresponding to these geodesics here. And these 2 ribbons behave the same way. They are, well, actually they are here and here. Okay, maybe the picture is a bit messy, but what you can check is that you have 4 rectangles here that arrive, and these rectangles do nicely 2 by 2. Here you have that one that goes here, and then in this part, this one here connects with that one. And in all these intervals, you have always 2 rectangles that glue nicely. So Birhoff gives us here a nice surface. What is important, what is interesting with this surface is that this surface is transverse to the geodesic flow. Why is it transverse? Because here, at every point, the geodesics go through the blackboard, so they are transverse to the surface. So our surface has the following properties. So the interior of S gamma is transverse in the geodesic flow. The boundary of S gamma. So what is the boundary of S gamma? The boundary of S gamma is exactly here the orbits, the lifts of the collection gamma. So ds gamma is the union of here 12 periodic orbits. 12 because we had 6 geodesics and you can travel in both directions. So 12 periodic orbits. Okay? And the most important thing is that S gamma, the interior, intersects every orbit of the geodesic flow. Why does it intersect every orbit? Because if you take any geodesics will travel, will go through black and white faces alternatively. And when it goes from a white face to a black face, it will intersect the surface. If you take a geodesic here that goes from a white to a black face, here at that moment it intersects our surface. And since the geodesic will not stay forever in the white faces, because it cannot, because these are disks, so you cannot stay for long here, all geodesics are intercepted by our surface. So this means that what we have constructed is a section for the flow, a surface that is transverse to the flow and intercept every orbit, except for the orbits that do the boundary of our surface. So if we remove these orbits, that is, if we consider the unit tangent bundle to our surface, and we remove these 12 orbits, what we are left with is our copy of S gamma. Our copy of S gamma that we can just push along the flow. And up to reparametrization, we can just assume that then we come back on our surface after time 1. We can assume that the time that the geodesics needs to go from one intersection to the left to the next intersection, we reparametrize this time so that it is always 1. And so we can identify this with just this modulo, a first return map. So you see that after removing just the boundary of our surface, what we are left is just, once again, a suspension. Okay. Now you can ask, what is the type of our surface S gamma? Here we have a certain surface. Well, I can do the computation for you. Actually, it's so S gamma is constituted of rectangles, actually of 12 rectangles because we have 12 arcs here. And you can check that each rectangle contributes to -1 to the characteristics. So you have that the Euler characteristic of S gamma is -12, and also the number of boundary components of S gamma is 12. So this implies that S gamma is a torus. A torus with 12 boundary components. So Birhoff has constructed for us a torus with 12 boundary components. And now what we can do is to wonder what is this first return map F. Well, what is nice is that this first return map F has an additional property here. Since our map is of Anosov type, there is this stable direction. So you can look at, you have the direction of the flow, and you have this stable direction made of those orbits that converge in positive time. So this gives you the two-dimensional foliation. And this foliation here contains the direction of the flow. So you have this two-dimensional foliation in your three manifolds, and you know that this surface here is transverse to the flow. So it's also transverse to this two-dimensional foliation. Which implies that here you can look at the intersection of this stable foliation with the surface. So here what you look is the stable foliation of the Anosov flow. So this stable foliation is by definition the direction spanned by the direction of the flow and the strong stable direction. And you intersect that with our surface. So this is a two-dimensional surface, this is a two-dimensional foliation, And this direction is transverse to the surface, so you have something that is transversal. So what you inherit is a one foliation of the surface. You have a one-dimensional foliation of the surface, and since this two-dimensional foliation was invariant by the flow, here this one-dimensional foliation is invariant by the first return map. So what you have here on S gamma, you have a torus with 12 boundary components, I go like that, and you have a one-dimensional foliation that is invariant by the first return map. And actually you have two of them because you have the stable one, and of course you have the unstable one, which is transverse to that one, so it looks like that. So you have two foliations on this surface, two transversal foliations on this surface. So here I don't tell you what happens around the boundary components, and it would be worth looking at it. But the picture is the following. If you look at the stable foliation, you see that it comes exactly like that. Here you have to trust me. So that actually, if you look at the first return map now, F. If you look at the first return map, the boundary components actually are invariant by the flow, so they correspond, you can collapse them into fixed points. Yes? And so now what you have is a map of the torus with at least 12 fixed points, and two invariant foliations. One which is contracted by the flow, and one which is expanded. And this tells you that actually F is conjugated to some torus automorphism. Because F is actually an Anosov map, and all Anosov maps are actually torus automorphism. And you can determine explicitly what is this F, and here this F has been computed, and it is this matrix in that case. So what does that tell you? That tells you that if you remove these 12 periodic orbits of the geodesic flow, what you obtain is actually equivalent to the suspension of this torus automorphism. So if I summarize, in general, if you have what is called a Birhoff section, so if F is a Birhoff section, and the Birhoff section is just what we constructed, a surface that is transverse to the flow but whose boundary is made of periodic orbits. If S is a Birhoff section, then the flow is almost equivalent to the suspension of the first return map on S. Okay, so every time you can construct a Birhoff section, you obtain an almost equivalent between your starting flow and a certain suspension. And if your Birhoff section is of genus 1, as it was in this example, then you obtain an almost equivalent between your starting flow and a suspension of some automorphism of the torus. Okay. And so now, how can we, well, now I can state a result. So, the question is, do we have many Birhoff sections? Maybe the first question would have been, can we have sections without boundaries? But here the answer is, in general, it's very hard to obtain sections without boundaries. But here we have a very nice theorem of Fried, David Fried, from 82, that every transitive Anosov flow admits a Birhoff section. So this construction that was done by Birhoff in this very particular case of a genus 2 surface, you can do it for any transitive Anosov flow. Yes, I put transitive. Yes. But in general, the sad thing with this theorem is that actually Fried has no control on the genus of what he constructs. This construction starts with a certain Markov partition of your flow, and if you don't have, if the Markov partitions are already complicated, you will end up with something with high genus. And actually it's a question, so I will put it as a conjecture once again, that actually you can, every transitive Anosov flow admits a Birhoff section of genus 1. So free to construct a transitive Birhoff section with no control on the genus, and it's still open to know whether you can construct Birhoff section with genus 1. But now assume you can construct a Birhoff section of genus 1, then what this gives you, exactly about what we said, this gives you an almost equivalence with a torus, with a suspension of a torus automorphism. And so here comes now my contribution here. The thing is that actually what you have is that every geodesic flow, so that means on the unit tangent bundle to H2 over gamma, so for every gamma for the geodesic flow admits the genus 1 Birhoff section. Okay, so first, every geodesic flow is like that, almost equivalent to some suspensions. And you have more, you have some control on the first written map, namely, I will state it like that. Every every matrix of the form what we call a companion matrix, in French at least. Every matrix of this form, 0, 1, minus 1t, for t larger than 3, is the first written map of some Birhoff section of some geodesic flow. And now what I claim is that with this second part, you can actually prove what I said in the beginning, or in the middle, that all automorphisms of the torus are almost commensurable. How do you do that? Well, I will illustrate that.
So can you tell explicitly what genus of the surface you should take to obtain specific T?
Yes, actually it will not be a surface, it will be an orbifold, but I can give you exactly the orbifold. I will tell you. Okay. Well, I was a bit sloppy here on what we consider. I always pictured a genus 2 surface, but actually the quotient need not be a surface. It can be a true orbifold with conic points. So what happens is that if you consider an orbifold, say, of triangular type, say this orbifold. So it means it's a sphere with 3 conic points, where here this point is actually a quotient of a disk by another 2 rotation, and this point is a quotient of the disk by another 3 rotation, and this point by another 7. Yes. So here, actually, the function groups here has a fixed points where it acts by rotations. So the stabilizer of that point is another 7 rotation group. But you can still look at the quotient here, which has some conic points. But what is nice is that at the level of the unit tangent bundle, it's still a nice manifold. Because if you look at the unit tangent bundle to say this disk, so the unit tangent bundle to a disk is just a full torus. Yes? Above every point you have a circle. Now if here you have a group that acts by rotations, by order 3 rotation, how does it act on the unit tangent bundle? Actually it acts by screw motion, because if you have a tangent vectors here, you have to rotate the base point and you have to rotate the vector. So which means that here, this rotation group on the unit tangent bundle, it acts by screw motion. So this point is sent here, this one here, and this one back here. Which means that the quotient of this unit tangent bundle, here if you take a solid torus and you quotient by a screw motion, you still obtain a full torus, a nice manifold. So what I want to say is just that here in this case, this thing is again a manifold. So here you have also a well-defined geodesic flow on this object. And now what I claim is that here if you put actually an R here, you will obtain a Birhoff section whose first return will be this matrix. So I put 2, 3 R here. R has to be larger than 7 in order to obtain an hyperbolic orbifold, and the matrix you obtain is just as trace R minus 4. So this is, well, of course I have to prove this theorem that there exists a Birhoff section with this first written map. And if you believe me for that one, then you obtain these things here. And using that, how do you obtain the almost equivalent thing? Well, you can obtain the almost equivalence like that. You start from a matrix A and a matrix B. So these are just some suspensions of some torus automorphism. As we say, there is a commensurability here of these things by a matrix of this form. And here by a matrix of that form, we have a different trace, not necessarily the same. And here what I claim here is that this one is almost equivalent now to the geodesic flow. This one is almost equivalent to the geodesic flow on the orbifold 2, 3, t minus 4. And this one is almost equivalent to the geodesic flow of 2, 3, t prime minus 4. And now these are two geodesic flows, so they admit a common covering by some certain surface of genus G. And so we all this way we obtain an almost commensurability between this suspension and that suspension. Okay, so I don't know what time it is, maybe I could end up quickly. Yeah, so maybe what I can do is just to present this construction here. This construction is not very difficult. So, how do we obtain it? Actually, here, so we have this orbifold, and it has a, what we consider is a geodesic starting from that point, and coming back here after one turn. And what happens when you consider these geodesics here, when it reaches the other 2 points, so here you are in this, locally what you see is that, you come to that point, so you continue straight, and actually up to another 2 rotation, what it is just taking the geodesics in the other direction. So going through these other 2 points is the same thing as going here and back. So when you reach here the point behind, if you go on, you just come back here. And when you reach this point again, so actually there is one periodic geodesic that just alternates here, that goes in both directions. What I claim is that we can copy our Birhoff construction using just these geodesics. So here we have one geodesic, and now what we do, so this geodesic separates the orbifolds in 2 parts, the parts containing that point and the other one. And now we just apply Birhoff construction here. So locally the hyperbolic plane, what we see is so this is a picture in the hyperbolic plane. We have some argon here and some triangles here and some argons here. And you play Birhoff construction, that is, you look at all tangent bundle, all tangent vectors looking in the black part. And this gives you a surface. So you just have those vectors here looking in the black part. And you have to check that at this point it behaves nicely, but it doesn't. Because what you obtain at that point is exactly the quotient of our picture at double points by another 2 rotation. And this picture is invariant by a rotation, so you have a nice manifold in the quotient. And what you obtain here is just a surface, S gamma. And now S gamma has just original characteristic -1 and 1 boundary component. Yes. So what you obtain, this S gamma here, is a genus 1 Birhoff section with 1 fixed point, at least. And now what you have to do is to compute the first return map on this S gamma. And this first return map, it's not very hard to compute. Well, it can be computed. Actually, here you obtain one surface, which I will call S black, which corresponds to those vectors pointing in the black face. And there is another one, a friend, which is called S white, which corresponds to those tangent vectors pointing in the white face. And it is another Birhoff section. Actually, there are 2. What happens is that the flow pushes the black one to the white one and the white one to the black one, because you alternate between black and white faces. And so you have a well-defined map from here to here, and then a well-defined map from that one to that one. Yes. And so here, say you have yeah. Okay. And now what you have to do is to look at what is this map. And it's a map, this map, and these maps are just maps of the torus. So what you do is that you take two loops on this torus, and you look at their images and how they intersect. You can do this computation, and what you find is that this map here is this matrix, 0, 1, minus 1, or minus 2, and with the same principle, this one is 0, 1, minus 1, 1, because this is just the r minus 2 in the case r equal 3. And if you compose these two matrices, you obtain the set. Okay? And now you can. Okay. So this is the proof of that theorem. But I think that, okay, what I wanted to say is this conjecture that does every. So this is the main conjecture I am interested in. So this conjecture is proven for geodesic flows, but now my question is for general transitive Anosov flow, what can you say about this conjecture? And if you can solve this conjecture with that one, that would imply that all Anosov flows are almost equivalent. Okay, so this conjecture of Fried is really interesting. Okay, I think it's time to stop.
Here is r minus 3 or r minus 2 because here
okay,
is
now this
minus 4.
This one is 2, but actually if you do the product of these two matrices, because the map is the composition, what you obtain here is conjugated to r minus 4. I mean this one, I don't know.
Okay.
You obtain, yeah, okay, so you obtain minus 1, 1. It's complicated. Minus r, and here I have r minus 2. And then this one has trace r minus 4.
Okay.
Other question? Please? No? Thanks again.
Так, что у нас в следующий раз будет